All right, let's talk about something we use every single second, but maybe don't really think about. That invisible force zipping through the walls, powering, well, everything. Our phones, our lights, our entire modern world. Today, we're going to take a journey right down the wire to actually understand what electricity is all about.
Seriously, take a look at the cord for your lamp or your phone charger. Just sitting there. Looks so boring, right? But inside that little plastic tube, there's a whole universe of chaos and energy. What is actually happening in there? What's moving? Let's find out.
It all boils down to just three big ideas. There's a constant flow, a really powerful push, and, believe it or not, a surprising little obstacle. Flow, push, and obstacle. That's the whole story. So let's dive in and meet these characters.
Okay, first up, the electric flow. So, this flow has a name, electric current. The best way to think about it is like a river, but instead of water molecules, you've got this massive rush of tiny charged particles, usually electrons. And just like a river needs a riverbed, this current needs a path. It has to be a complete, closed loop with no breaks. We call that an electric circuit. And a simple flashlight, it's a perfect example of this. You've got the battery, the little bulb, and the switch. They're all part of this potential loop. When you slide that switch on, bam! You've just lowered the drawbridge. You've completed the circuit. The current can now flow from the battery, right through the bulb, making it light up, of course, and then all the way back to the battery. Flick the switch off, you break the path, and the lights go out. Simple as that. All right, so we've got the flow, the current. But what makes it flow in the first place? And is there anything that gets in its way? This is where our other two characters come in, the push and the squeeze. Yeah, these little charges, they're not just going to move for fun. Something has to shove them along. So what is that shove? Well, that push has a fancy name, electric potential difference. But you and I, we just call it voltage. It's basically electric pressure. It's the force that gets all those charges moving, and it's created by something like a battery or the power grid. This water analogy is probably the best way to get a gut feeling for voltage. Imagine two connected water tanks. If the water's at the same level in both, nothing happens, right? But the second you raise one tank higher than the other, the difference in pressure makes the water flow. A battery does the exact same thing, just with electricity. It creates a high pressure point at one end and a low pressure point at the other, and that difference is what pushes the current around the circuit. Okay, now for the squeeze. It's not a perfectly smooth ride for those electrons. As they're zipping through a wire, they're constantly bumping into and crashing through the atoms of the wire material. This opposition, this traffic jam, is what we call resistance. It's basically electrical friction, and it slows the current down. Every single material has it. And the difference between materials is just mind-blowing. Look at this. Copper, on one hand, is like a 6-lane empty superhighway for electrons, barely any resistance at all. But then you have glass. Glass has a resistance that isn't just double or triple, it's billions upon billions of times higher. It's a total dead end for electricity. And that right there is why our wires are made of copper on the inside, the highway, and wrapped in plastic or rubber on the outside, the solid wall. So, we've met our cast of characters, the current, the flow, the voltage, the push, and the resistance, the squeeze. They're all connected, and there's one simple, beautiful rule that ties them all together. Let's get into the law of the circuit. This all goes back to 1827. A German physicist named George Simon Ohm was messing around with this stuff, and he figured out this absolutely fundamental relationship. He realized that the push, the voltage, is directly connected to the flow, or the current. The more you push, the more flow you get. I know, it sounds kind of obvious to us now, but back then, it was a total game changer. And it all comes down to this one elegant little equation. V equals I times R. Voltage equals current times resistance. That's it. That's the golden rule. These three things are locked in a dance. If you know any two of them, you can always figure out the third. This single formula is the key to understanding pretty much every single electronic device you've ever touched. Okay, let's make this real. Look at this chart. You've got an electric heater and a regular light bulb, both plugged into the same 220-volt wall outlet. So the push is identical for both. But look at the flow. The heater has really low resistance, so it just guzzles current, pulling a whopping 2.2 amps. The light bulb, though, has a super high resistance filament, so it only sips a tiny bit of current, just 0.18 amps. See? Same push, but
but a different squeeze results in a totally different flow. That's Ohm's law in action, right there.
Okay, so that's how it works with one thing. But what happens when you start adding more stuff to a circuit, like multiple light bulbs? Well, there are two main ways you can wire them up: series versus parallel. And trust me, the way you choose changes everything. Think of it like roads. A series circuit is like a one-lane country road. There's only one path, and every car has to go through every single town, one after another. The current has to pass through every single component. But a parallel circuit? That's more like a highway with multiple exits. The current gets to the first component, and then the path splits, giving it choices of which way to go. And this simple difference totally changes how the current and voltage behave, and even how the total resistance works. Okay, here's a question that I'm sure has driven some of you crazy. You know those old holiday lights, the ones where if a single tiny bulb burns out, the entire string goes dark? Why on earth does that happen? It's because they're wired in series. Remember that one-lane road? If there's a roadblock, like a burnt-out filament in one bulb, the entire road is closed. The circuit is broken. The current has nowhere to go, so it stops, and every single light goes out. It's a huge pain, and it's exactly why your house is wired in parallel. You wouldn't want the fridge to shut off every time you turned off a lamp, right? Okay, so we get how electricity moves around, but what about the work it does? The reason we use it in the first place? Let's talk about the power we actually use. You remember that resistance, that squeeze we talked about? Well, all that bumping and crashing, all that friction, it generates heat. A lot of it. This is known as the heating effect of electric current, or Joule's law. And the formula is pretty simple. The more current you force through something with resistance, the hotter it's going to get. And the longer you do it, the hotter still. And it turns out we use this heating effect on purpose all the time. Your toaster, it's literally just a bunch of wires that are designed to have high resistance. You run current through them and they glow red hot. Toast. An old school incandescent light bulb, same exact principle. It forces a ton of current through a tiny, super resistant piece of tungsten until it gets so white hot that it lights up the whole room. And the amount of energy we're talking about here is just immense. When you look at your electricity bill and see 1 unit, that's 1 kilowatt hour, that single unit represents 3.6 million joules of energy. To put that in perspective, that's enough juice to run your toaster nonstop for an entire hour. So this all leads to a really interesting final question. We started out talking about resistance as this obstacle, this squeeze that gets in the way of the flow. But then we saw that it's the very thing that lets a toaster work or a light bulb glow. So what is it? Is electrical resistance a bug or is it a feature? The weird answer seems to be it's both.